Somewhere in the western Pacific Ocean, about 200 miles southwest of Guam, there is a spot on the map that looks completely ordinary from above. Just water. Endless, flat, unremarkable water. But beneath your feet, if you were standing on that ship, the seafloor is nearly 7 miles straight down. That place is called Challenger Deep, the deepest known point on Earth. Not in a submarine, not in a pressure suit, just you as you are right now. What would actually happen to your body? Not in vague terms, but second by second, sensation by sensation, all the way to the bottom. The answer is far stranger, far more violent, and in one genuinely surprising way, far more fascinating than almost anyone expects. The moment you go under, the first thing you notice is pressure. At the surface, the atmosphere presses on you at about 14.7 pounds per square inch. That's what we call one atmosphere. You felt this your whole life, and you never notice it because your body pushes back with equal force. But the ocean adds one full atmosphere of pressure for every 33 feet you descend. So the deeper you go, the math becomes brutal. By 30 feet down, about the depth of a typical scuba dive, you're already at 2 atmospheres. You'd feel your ears screaming at you to equalize. By 100 feet, recreational divers start to feel the first hints of nitrogen narcosis, a strange dreamy euphoria sometimes called the rapture of the deep. But you're not stopping at 100 feet. You're heading to 36,000. Here's where it gets immediately dangerous. Without a breath hold or equipment, you have maybe 2 to 3 minutes of consciousness before hypoxia takes over. But set that aside for a moment, because what pressure does to the body structurally is the real story. Your lungs, sinuses, and the air spaces in your body become the enemy. Every air pocket you carry inside you is a liability the deeper you go. At around 90 feet, your lungs, which hold roughly 6 liters of air at the surface, have already been compressed to about half their normal volume. By 300 feet, they're the size of a fist. Freedivers actually train for this phenomenon called lung squeeze, and some remarkable humans have survived it. But at 300 feet, you are not even 1% of the way to Challenger Deep. Around 600 feet, the edge of the twilight zone, sunlight vanishes completely. The world goes perfectly black, except for the ghostly blue and green flickers of bioluminescent creatures. It's hauntingly beautiful. But your body is already in serious structural trouble. The air spaces in your sinuses are being crushed. The pressure is working on your eardrums with a force that at this depth would rupture them violently. You would hear a sudden crack, then nothing. And here's something most people never consider: your eyes. The eyeballs themselves contain fluid, and fluid, unlike air, is largely incompressible. That actually works in your favor, oddly enough. But the soft tissue surrounding your eyes, the sinuses, the nasal cavities, those are a different story. The pressure differential between the compressed air pockets and the fluid-filled tissue causes something called a squeeze, and without protection, the results are severe internal hemorrhaging. By 3,000 feet, the midnight zone, you have entered a world where no sunlight has ever touched. The temperature here hovers just above freezing, around 35 to 37 degrees Fahrenheit. Your body would be losing heat at a catastrophic rate. Hypothermia would be compounding every other trauma. But here's the thing, at the pressures you're now experiencing, roughly 90 atmospheres, the cold and the hypothermia are almost secondary concerns. At 90 atmospheres, every square inch of your body surface is experiencing about 1,320 pounds of force pushing inward. Think about that. Not 14 pounds like at the surface. 1,320 pounds per square inch. Your rib cage, which evolved to protect your lungs and heart, would begin to deform. The cartilage and bone can only resist so much. Competitive freedivers have experienced rib fractures from pressure alone. You are nowhere near the bottom yet. But now comes one of the most counterintuitive facts in all of deep-sea science. And this is the mid-video twist that will genuinely reframe how you think about this. You might assume that as pressure increases, your body would be shredded, torn apart, explosively destroyed. But that's not quite what happens. And the reason comes down to the difference between what's inside you and what's surrounding you. Here's the key. Pressure, on its own, doesn't necessarily destroy soft biological tissue the way we picture it. Water, which makes up roughly 60% of your body, is essentially incompressible. It doesn't get smaller under pressure. So the watery tissue of your muscles, your organs, your blood, they actually transmit pressure relatively uniformly. Deep-sea creatures have virtually no air spaces in their bodies at all, which is why they can survive at these depths. The problem for you is everything that isn't water. Every air space in your body, your lungs, your sinuses, the tiny air pockets in your digestive system, becomes a catastrophic pressure differential waiting to collapse. At extreme depth, those spaces don't just compress, they implode inward. The surrounding tissue rushes to fill the void. This is called barotrauma, and at the depths we're discussing, it would be total and catastrophic across every air-containing structure you have simultaneously. James Cameron descended to Challenger Deep in 2012. Victor Vescovo reached it in 2019. They were sealed inside titanium and steel spheres designed to withstand the pressure. Even then, even with all that engineering, their craft groaned audibly under the load. The pressure at the bottom of Challenger Deep is approximately 1,086 atmospheres. That means roughly 15,900 pounds pressing on every single square inch. To put that in human terms, it's like having 50 jumbo jets stacked on top of you. Here's a simple demonstration that scientists actually use to show this effect. Attach a styrofoam cup to the outside of a submersible and send it to the bottom of the ocean. When it comes back up, it's been compressed to roughly the size of a golf ball, perfectly intact, just miniaturized. Every air bubble in the foam crushed out. That's what pressure without destruction looks like on something with no structural integrity to resist. Your body, in many ways, would undergo something similar in its airspaces. So let's trace the full descent. By 1,000 feet, you have lost consciousness from hypoxia long ago. By 3,000 feet, your lung tissue has hemorrhaged. Your sinuses and middle ears have imploded. By 10,000 feet, you're in what's called the abyssal zone. Temperatures near freezing, pressure exceeding 300 atmospheres. Your body is being compressed uniformly in its fluid parts, while its air spaces have long since collapsed entirely. By the time you approach the Hadal zone, below 20,000 feet, you're entering a world so remote and hostile that fewer humans have been here than have walked on the moon. The seafloor of Challenger Deep is covered in a soft, pale sediment called Hadal ooze, the compressed remains of billions of years of dead organisms that have slowly drifted down from above. It's oddly peaceful looking, almost lunar, and it's not lifeless. Tiny crustaceans called amphipods have been found in abundance at Challenger Deep. They are thriving, active, perfectly adapted, their cells packed with special molecules called piezolites that prevent proteins from being crushed and denatured under pressure. Life found a way. But your cells carry none of those adaptations. Here's another twist that physicists find fascinating. At the pressures of Challenger Deep, water itself behaves slightly differently. It becomes measurably denser, about 5% denser than at the surface. This means the water you're being compressed by is itself a bit more tightly packed than normal water. It's a strange, alien form of the most familiar substance on Earth, and you're immersed in it completely. At 36,000 feet, the very bottom, the pressure on your body would be 1,086 atmospheres, or about 15,900 pounds per square inch pressing inward from every direction simultaneously. Your body's fluid components would still be mostly intact. The physics of incompressible fluid means your muscle tissue and blood wouldn't simply disintegrate. But every cavity, every hollow space, every air-filled structure would be gone, crushed completely flat, filled in, erased. In one genuinely strange sense, a body at that depth might look largely intact from the outside, especially after the slow descent causes the remaining gas to escape and the body to reach a neutral density. Deep-sea explorers have theorized that an unprotected body at extreme depth would eventually become something closer to a dense, compressed mass, not the Hollywood image of being torn apart, but something more like being slowly, utterly, and completely collapsed inward. This is actually why deep-sea rescues and recoveries at extreme depth are considered effectively impossible for an unprotected human body. The pressure changes during ascent, once a body has equilibrated to depth, would cause catastrophic expansion and damage in reverse. The bends, also known as decompression sickness, would be unsurvivable without an incredibly controlled, hours-long ascent. At these depths, there is no rescue. And yet, and this is what makes Challenger Deep genuinely one of the most extraordinary places on the planet, it is not hostile to all life. It is not a dead zone. Bacteria thrive in the sediment. Amphipods swarm food sources within hours. Snailfish, a pale, ethereal-looking fish with no scales, had been filmed at depths below 26,000 feet, the deepest fish ever recorded. Life doesn't just survive down there. In some ways, it's flourishing. The snailfish is perhaps the most mind-bending creature in this story. At a depth that would collapse your lungs, rupture your sinuses, and crush every airspace in your body into nothingness, this translucent, almost fragile-looking fish is simply swimming, eating, living its life as if 15,000 pounds per square inch is just another Tuesday. It has adapted over millions of years to call the most crushing environment on Earth its home. This is the part that should make you pause. The ocean's deepest point and the ocean's sunlit surface are separated by about 7 miles, less than the distance of a morning run. But they are as different as any two environments our planet offers. One is warm, bright, and built for creatures like us. The other is cold, crushing, lightless, and built for something we can barely imagine. Both are on the same planet. Both are filled with life, just not the same kind. So what would your body feel like at Challenger Deep? The honest answer is, you would feel nothing by the time the most dramatic events unfolded. Consciousness would go within minutes, but the physics would continue. Your body, mostly water and therefore mostly pressure resistant, would be slowly, completely reconfigured by 15,000 pounds per square inch into something unrecognizable. Not exploded, not shredded, just relentlessly, utterly compressed into the silence of the deep. The deepest place on Earth is right here on our own planet, accessible, mapped, and still almost entirely unexplored. We know more about the surface of Mars than we do about the bottom of our own ocean, and somewhere down there, in the dark and the cold and the impossible pressure, life is going about its business, utterly indifferent to the fact that we can barely imagine its world. Which raises one final question worth sitting with. If life adapted to the most crushing environment Earth could produce, what other impossible places might life have already made its home?